All right. Well, happy Friday, everybody. It is Friday of 8th week, which really just kind of means, I don't know, things are winding up and accelerating and whatnot. I don't know if you guys have final projects for other classes or just like, um, but well, so I hope things are things are going okay. Yeah. I've said this a few times, but I'm just kind of like ready for this quarter to be done. Although I'm like dreading just the amount of work that I have to take care of between now and the end. So, but I'll try to be mindful of everything. And for some of you, this is your last quarter ever at UCLA, which is also exciting. Maybe a little bit sad that your last quarter is spent online. And well, anyway, I don't know. There's a lot of things. Okay. Well, today's lecture is a little bit different. I just kind of have this notebook. Let me see if I can increase my font size. Let's see. I actually don't know how to text editor for font size. No. Settings, increase terminal font size. Does that do anything? I don't know how to do this. Increase. How do I increase the font size on this thing? Okay, well, I can just zoom in like this. Ooh, it's a little too much. Okay, well, we can hide these sidebars. Seems to be pretty good. Okay, so I just have kind of this notebook that I was going to work through, at least kind of just introducing just the very basics of Scikit-learn. Okay, so Scikit-learn. So just kind of we're covering like a hodgepodge of topics in Python, and so a while back we did stats models, which was kind of for traditional models, statistical models where you're fitting like linear regression, logistic regression, things like that. And the other package that's very popular in Python is Scikit-learn. Okay, and so you can just kind of Scikit-learn, and this is kind of the most popular package for machine learning, and it can do all kinds of stuff, right? So it's designed for any kind of supervised, unsupervised learning, as well as a bunch of things that are necessary. There's pre-processing, dimension reduction, model selection, all of these types of things, and the different models that you can kind of fit, right? So you've got classification, which is supervised learning, regression, which is supervised learning, and then you have kind of these unsupervised learning methods, clustering and dimensionality reduction. And then as far as getting your data ready, there's pre-processing, and then once you fit a model, trying to decide which ones you want, there's model selection. And so there's all sorts of stuff in this machine learning package. For some of you, I imagine a lot of you, you don't have like maybe a ton of machine learning background. If you've taken 102B with me, I cover some machine learning ideas and concepts. But if you've only taken stats 20 and stats 21, this is not a machine learning course, but I'll try to introduce at least some general ideas and concepts, at least kind of describe and talk about them. And in a lot of so for classification and regression, classification is all about right here, identify which category an object belongs to. And regression is basically predicting a numeric value, right? So if you think about what kind of response variables you can have categorical variables. And if you're trying to predict a categorical variable, that's going to be a classification problem. If you're trying to predict a numeric response variable, that's going to be a regression problem. That's effectively what it boils down to. And here today we'll talk about what we call supervised learning. Supervised learnings means you've got answers and you're going to make predictions. So when you quote train your model, which it means you're trying to figure out what values to use in your model. You have the answers, you know what what the answers are supposed to be. And during the training process, you take your inputs, you put them in through the machine, and it spits out predictions. And you compare, my machine predicted 5, the true answer was 6. And you say, okay, that's off by 1, right? Or, and then you say, okay, well, let's fix this, right? And then, you tweak the values that go inside the machine. You take your input and it says, okay, now that we've tweaked them, now it's predicting 5.5 and the true answer is 6. And we say, okay, well, 5.5 is closer to 6 than 5 was. So this is an improvement. This is a step in the right direction. And you effectively do this at large scale. You just have thousands or millions of observations, and you're trying to get the predictions for each of these observations as close as you can to the true values that appear in your data set. And that's basically what it comes down to. Okay, I won't talk about clustering or dimension reduction right now. Okay, so there's a whole bunch of stuff with Scikit-learn, and we'll just kind of take a look at some basic ideas here. Okay, so if you've installed Anaconda, Scikit-learn will be already installed, and you can kind of just get it into your machine by running import Scikit-learn. There's so many kind of like modules, so many different functions and things in Scikit-learn that generally you're gonna want to import specific aspects, specific programs or things from Scikit-learn. Okay, so anyway, you can do import Scikit-learn, and you get sklearn. And so right now you can ask for your version using _version. And I get version 24.1. I don't know what is the latest version today? Okay. April 2021, 24.2 is the latest. So you can always kind of update things. We didn't really talk about virtual environments in Conda, or, you can always set up virtual environments. But a lot of times when you use a package like Scikit-learn, it's advisable to create a virtual environment, just because these packages get updated every few months. You can see you had May 2020, August 2020, December 2020, January 2021. Updates are constantly kind of streaming, and sometimes the updates will break earlier versions of your code. And so if you want to kind of like take your answers or your notebook and pass it along to someone else, if they have the wrong version of Scikit-learn, it might not work on their machine. So it's often advisable to create a virtual environment. And then a virtual environment is basically a list of all of the packages that you're using and the exact versions of the packages that you're using. And basically, when you send something over to someone else, you send it along with the list that says, please install this exact version of Scikit-learn. And then, they'll set up this quote virtual environment, and it will download, the old versions or the correct version of the package. And so that's helpful. You can read about, how to set this up. There's a tutorial on Data Camp under Conda on setting up virtual environments and things like that. That's helpful. I didn't assign it in your homework or anything like that, but back in like week 1 and week 2, when we were talking about Conda, I think I assigned a assignment 1 chapter from Conda, and there's more chapters in that kind of same course that covers virtual environments. Okay, but anyway, this is the version that I'm using, and I'm just going to be using some very, very, very basic tools today. Okay, and so one is we're going to set up a linear model. Okay, and linear regressions, linear model. It doesn't have the nice appeal that it doesn't sound as fancy as some of these other machine learning models that we have, but a linear regression model does fit all of the kind of requirements of what machine learning is. Machine learning is basically you have some kind of measure of loss, some kind of measure of error, and you're trying to minimize that. You're trying to find the parameters that minimize that. And so as far as linear regression, you're trying to find your slope and your intercept that will minimize your measure of loss, okay? And so from Scikit-learn, we're going to import linear model, okay? And then there is, under Scikit-learn, there's this section called metrics, and this contains all of the kind of tools that we use to measure the performance of a model, okay? And so you have, from there, we're going to request the function that will measure mean squared error, as well as the function that will give us an R² score, okay, your R2 score. And again, you can always read a little bit more about this. So under model selection, under metrics, you have this. And then under regression, we have, oh, I don't know where it is. Under regression, we have linear models, and there's all kinds of stuff. So you're, if you haven't noticed, I'm a big fan of recommending reading the documentation. And there's the problem is there's just so much documentation, but we should be thankful, because nothing is more frustrating than trying to use a package that is poorly documented. Thankfully, Scikit-learn is, I would say, is very well documented. Every little function and thing, very good documentation. So you can, under metrics, this is kind of quantifying the quality of your predictions is basically what this is all about. And there's also all sorts of things as far as, measuring, your ROC score, if we're talking about classification, and for regression, we have all sorts of things, right? There's mean squared error, but then there's all sorts of other things as well. So we'll just kind of stick to the basics here. Okay. All right. I'm going to load up a data set. This is a data set that I've used in my 102B class. And this is, these are race times from the Olympics, where they measured the speed of the time of the gold medal 100-meter race. Okay, so people run 100 meters, the 100-meter dash, and they measure how long did it take for these people to run. And so, in 1896, I guess the gold medal time was 12 seconds. Okay, and progressively, as time has kind of gone on, people have gotten faster and faster and faster, right? And so 1968, kind of that 10-second barrier was broken, and we had somebody who ran the 100 meters in 9.95 seconds. And it wasn't, and that record wasn't broken until 1988. And, kind of consistently, we've been, not we, but people have been able to, run this foot race a little bit faster and faster and faster. Okay. So, so here I'm just kind of loading in the data using pandas read_CSV, and then giving names to the columns here. Okay, and then we're going to create a plot of this just using matplotlib. All right, so I've imported matplotlib, pyplot as PLT, and so this is nothing special. So this is just kind of a scatter plot, and we just see, over time, there seems to be general linear trend. Okay, obviously at some point this will level out, where we've reached the limits of human performance, but because obviously if you continue this on forever, we're going to reach negative times, which obviously is not possible, but and there will be a limit to how fast humans can go. Okay, and so what we're going to do is we need to shape our data in in a format that Scikit-learn likes. Okay, and so Scikit-learn expects all of your predictor variables, all of your X values, to be in a matrix, and it expects all of your response values, your Y values, to be in a one-dimensional array, or like a vector. Okay, so here if I just take the column Olympic.time, which is really just this thing, we're just kind of predicting this thing. I can extract that, I can ask the shape, and this is the shape that we want. We want it in a one-dimensional array, which is what we want. Okay, And so, thankfully, a lot of the aspects that all of these kind of packages run on, NumPy and pandas, they all kind of work a lot of times in the ways you want. Okay. It's interesting. So in Python, you have a whole bunch of different packages and modules, but there's just kind of a few primary ones that people contribute to. And so, and a lot of just kind of the ecosystem is a little bit different, right? So in pandas, or in Python, effectively, all of your data science notebooks are going to start off with kind of these things. You're going to see NumPy, you're going to see pandas, you're going to see matplotlib, and then you'll see sklearn. Okay, maybe you'll see stats models, maybe you'll see seaborn and things like that. But they're all kind of built off of each other. Versus the R ecosystem is there's like a tiny little package that just has like a few functions, and you might end up like calling so many different libraries every single time, where almost any notebook you open in R, you probably have to install a new package because it's going to be something that is less commonly used or something. And so it's just kind of different. You have the kind of the central authority in Python, and ours is a lot more distributed, just different different setups. Okay, so as far as creating a linear model, okay, all we're going to do is we're going to call linear underscore model, which is what we've imported from sklearn. So under sklearn, so the hierarchy is when you do, say, a linear model, it's under, sklearn.linear regression, okay? And we've already imported linear model, so we're going to just do linear regression. So we're going to run linear regression, and here we're going to tell it we want to fit an intercept, okay? If we could also have set up our matrix to kind of have a column of constants to fit the fit our intercept automatically, but here we're going to say, not only fit this variable year, but also fit a separate intercept. Okay, so this initializes our model. This actually could be, this doesn't need to be executed. All right, and the X, it needs to be a matrix. All right, and so if I take olympic.year.values, okay, this is going to be just a one-dimensional array, a lot like, say, olympic.time. But here I need to reshape it into a matrix, okay? And so reshaping the, I'm going to reshape it to be one column, okay? And the -1 here just means, I don't want to be bothered to calculate how many rows it's going to be, right? So here, from looking at the Y shape, right, x.reshape, 28, 1, okay? I could write 28, 1, but using the -1 just tells Python, all I know is I want one column. I don't actually know how many rows I have. You figure it out, okay? And so when you give it a -1, it's Python or NumPy is going to figure out what exactly needs to go in that spot, okay? And then, and so when we do this, we're going to get a 28 by 1, 28 by 1 thing, okay? And that's what we want, right? If we gave it this, if we didn't do the reshaping, we would have a 28 comma. We would have just a one-dimensional vector. Why did I do olympic.year.values here? So let me see. I think if I do olympic.year, I'm going to get back. Let's just see. Okay, Olympic. Yeah, I have a series. Let me just do a shape. That's fine. I guess let me just see if I can I reshape this into yeah, so if I don't, yeah, so Olympic.year, as it is a series, I believe, right? So let me just see. Type on Olympic year. This is a series, and you're not allowed to reshape a series, okay? So the series will, it does have the shape, okay? So I could, so Olympic.time, Olympic.time looks like this. And if I can ask for the shape here, and it's 28, okay, which is exactly what I have here. I could also ask for Olympic.time.values, all right, and I get this array, and I could ask for the shape, and it's also going to be this, okay? The issue, the reason why I didn't bother doing time.values is this is already in the shape I want it, and it's fine, okay? If I don't take, and it comes with this thing, Olympic.time comes with the index, right? So when you do Olympic.time, it comes with the index, and if you do values, it drops the index, and you just have the array of values. Whereas over here with the year, if I take the year, it comes with the index, and you are not allowed. Like if I try to reshape this to 28 by 1, it's going to say you're not allowed to do that. Okay. However, when you take the values, you can reshape it. Okay. So the reason why, good question, is here it's already in the shape I want. Here, if I take the year, I'm not allowed to reshape it. But if I take the values, I am allowed to reshape it. Okay. So it just, stuff like that, right? Because basically we want to rearrange stuff, and when you reshape it into a matrix, there's going to be no index kind of associated with it. All right, I hope that makes sense. Okay, so now we have our X matrix. It's in the shape 28 by 1, 28 rows by 1, and now we can fit the model. Okay, so we're going to fit this model that we've created between the X matrix 28 by 1 with our length 28 array. Okay, and that's it. Okay, and then we fitted our model. Okay, now if you want the coefficients, you can get that. Okay, so you can ask for the resulting model coefficients. All right, and so here it's going to give us the associated slope. All right, and so this is going to say, for every increase in X, the year, we expect the time prediction to go down by 0.013. You can also ask for the intercept. This would be our predicted time in the year 0, which, doesn't make sense. Okay, but what we can do is we can kind of ask for something like, let's make a prediction for the winning race time from the year 1900 to the year 2000. We're going to create a linearly spaced vector, right? And so when we do this, we're going to get a vector, basically 1900, 1901, 1902, all the way up to the year 2000. All right, so this is just creating a vector of values using NumPy. And then down here, what we will do is we will ask the model to make predictions, okay? And in order to make predictions, what we have to do is we need to, again, reshape it to be the same, at least have the same number of columns as our input X, okay? So in our case, we need this to be an n by 1, because that's how our input matrix X is. Our X is n by 1. So we need to create our prediction vector or prediction matrix to also be n by 1. Okay, so we'll do that. So if I do this, this will be 101 by 1. And then I'm going to ask, now that I fit the model, we can make predictions for some new matrix, new input matrix X. Okay, and so here's now kind of all of the predictions that we get. Okay, so all we're doing right now is we're just going through the kind of the cycle of, we have some input data for training. We fit the model to our training data. We get the resulting fitted model. Now we're going to make predictions based on this. Okay, and so let's see if we can make a scatter plot. Okay, so what we're going to do is we're going to create a scatter plot between the original X and Y, all right, which is our observations. And then we're going to add a line that shows the fitted values that go from kind of the year 1900 to the year 2000. Okay, so all we're doing is the blue dots represent our fitted, our actual values. And then the red line is kind of our prediction line for 1900 to 2000. And we can see this is a straight line. Okay, and if we wanted to, we can ask for the residuals. Okay, and again, Scikit-learn, it comes with a bunch of tools for model selection, but these take kind of a strictly machine learning approach for model selection. These will not include kind of your classical methods of evaluation, right? So your classical methods of evaluation for fitting, evaluating a linear model would be things like checking your residual plots for heteroscedasticity and checking to see if they're normally distributed or things like that. That's not part of Scikit-learn's philosophy as far as checking models. Scikit-learn takes almost a strict cross-validation approach only as far as checking to see if your model works. And I don't know if I created a secondary thing, but I don't know if we'll have enough time to get there. But next week, we'll talk a little bit about cross-validation and, train test split, which is basically how Scikit-learn's approach as far as evaluating model selection. But, if you wanted to kind of look at your residuals, you can do that. We're going to just take the difference between our actual values y, what our x thing predicted, okay? And so here we can only really evaluate differences between the predictions for the x values that do exist, because these are we only have actual values for those values in here. So we can create that. That's going to be our residuals. We can see what those values are, what those residuals are. We can ask, what's the mean of our residuals? And in linear regression, the mean of your residuals for your training data is always going to be 0, and we effectively get basically the equivalent of 0, but with floating point precision. We can create a histogram of our residuals, which it seems like there is a significant outlier, which would be this observation. Okay, so that could be an indicator of something, perhaps we have something problematic, maybe not, who knows. Okay, so we will want to take that into account, because this outlier, this observation certainly is an outlier. So maybe we want to redo our evaluation with this observation removed. And I think you could justify removing that observation because it seems to be from a time where who knows how accurate the stopwatches were in 1896, or how we measured time in 1896. 1896, 1900, 1904, it just seems like the times were measured to the nearest second. So, was this really 11 seconds or was it 11.4 seconds? It's really hard to say, right? At least in 1906, we started able to measure fractions of a second. So whatever happened and however stopwatches worked, we had some kind of thing here, right? And now when you look at the race times, they have those super slow motion cameras right at the finish line, and they can see exactly when the person's body crosses that plane of, the finish line and whatnot. And it's, they really come down to it. But, before it used to just be people standing at the, when they had like physical stopwatches, they would stand at the finish line and they would just look and they would just click as soon as the person crossed, and, lots of measurement error, right? Okay. So anyway, you can create a plot of the residuals themselves and just see like, okay, this is what we have. And certainly this is an outlier. I'd say we should get rid of it. Okay. So anyway, that's the very basics of that. I have another kind of similar data set here where we can take a look. This is the Boston housing data set, which is a problematic data set in of itself. But in the stats world, there seems to be like certain data sets that are commonly used just because they have nice things, right? Like the iris data set, you constantly see that pop up everywhere, just because it's nice and it's easy and handy. But it's always good to kind of pause and think like, why was this data even recorded in the first place? I've totally forgotten to give you any kind of view quiz answers today. So let me go ahead and give you some. First view quiz answer, let's do your first two. First two view quiz answers today are D and E. D as in dog, E as in elephant will be our first two view quiz answers. D as in dog, E as in elephant. Okay, and then so the Boston data set, this this was recorded like in the 1970s. When was this? Where is the data on this? Scikit-learn. What's it called? Boston. Let's just search Boston. Load Boston. That's it. They don't have load Boston, read more in the user guide. Oh, here we go. Okay, so it's a copy from this data set, but this is, if you read the a little bit more on the data set, it's just like, ooh, I don't know if this is a good data set. But they're kind of looking at different variables. Okay, the median value is often the target. Okay, and this is the median value of owner-occupied homes in the thousands. And what we're looking at is no, that's not what I want. Okay, that's not very helpful. All right, everything's reported as the same. Okay, well, what we can do, so some Scikit-learn comes with kind of its own data sets loaded in, and they're good for at least like learning the tutorials on Scikit-learn. Okay, but doing actual data projects, I recommend using a more interesting data set. And so, well, okay, this is just a bit of general advice, not specific to this course, but a lot of students ask about like, how can I do some kind of project, or what can I do to make myself an attractive candidate for jobs and things like that. And so I think doing your own data analysis project, not part of class, that doesn't just necessarily follow some tutorial out there, can speak a lot. And it could be anything that you're kind of interested in, anything that you have a little bit of knowledge about, is probably a good place to start. There are lots of data sets out there, and you can go across the internet and you can search kind of these machine learning websites. UCI has a big database of different data sets, and you can also go on Kaggle to find data sets out there. But a word of caution, a lot of data that's on Kaggle is total junk and trash, because people will do like web scraping projects, and they will go out and they'll scrape the internet to kind of gather this data, and that's a reasonable thing to do. But you just have to be careful, because when you scrape the internet, there is a lot of junk and trash, and so it's a bit it's hard to you have to be careful. And so basically, just make sure you take the time at least half an hour of actually going through the data set itself, going through line by line, and just kind of asking, does this observation in the data make sense, right? And so hopefully it's a subject that you're kind of familiar with, so that when you look at an observation, you can say, ah, yes, this makes sense, right? So for example, somebody was interested in like League of Legends, and they were really into it, and so they were able to look at a data set, and they were able to kind of look at the lines, because each line represented a game that was played, and like and the numbers that appeared, they could say, oh yes, this makes sense. And they could also identify certain lines which didn't make any kind of sense, right? Because apparently like it recorded like the time that something happened in the game, and I'm not very familiar, but they said it doesn't make sense that the time that the first tower fell was this number, because that's something like that. So anyway, it's got to be something that you got to be kind of familiar with, otherwise you'll be just working in the dark. So make sure to spend a good amount of time to kind of just go through asking, does the data make sense? Okay, anyway, the data that comes in the data sets in sklearn, these are known as bunches, okay? So if you go in and you load up a data set, it comes in as a bunch, okay? And basically, a bunch is, it's like a dictionary, okay? It's like a dictionary, except the values in the dictionary are going to be different kind of data structures. It's not necessarily just one kind of thing. It's going to be so within this bunch, you have a key for the data. Okay, within the data set, you've got the data itself. You have the target value. So the data represents your X matrix. Target represents kind of your Y values that you're trying to predict. But it also comes with other things such as the feature names, the names of the columns in X, the description, and things like that. Okay, so if I take boston.data, okay, that's going to be our X variable. X comes back and says, oh yeah, that's a matrix, 506 rows, 13 columns. Okay, and then if you take the target, which is the values that we're trying to predict, that's going to be a one-dimensional array, 506 values, right? You can also print out the feature names, which is comes in like this. So this is what you can use as kind of your column titles. You can also ask for what's the description of the data, and it comes back, and it comes with all of the information that summarizes these things, right? So when I look at this description, they have like racial information, and just like the way they describe it is like, oh, I don't, and the data is stored, at least in my thing where Anaconda is installed in my computer, and under my file name here, it's stored in this CSV file. Okay, so anyway, it's when you take a boston.data, it's an array. And what we want to do is, I'm going to turn it into a data frame, okay? Because the array itself is not going to have any kind of column names. So what you can do is you can just kind of do, you can create a data frame out of it. So using a pandas data frame, you do pandas.data frame, make a data frame out of boston.data, okay? But now you have a bunch of columns that have no name, right? And so easily what we can do with pandas is we can just take boston.columns and take the feature names, which are stored in this vector, and just add that to the data frame. Okay, so we have this, and so now we have a data frame that seems a little bit more reasonable. We can also take the kind of the values, and we can add we can take this target and add it to the data frame itself. So we can say, all right, we know that the target value is the price, okay? And so we can say boston.price is equal to boston.target, and that's going to add that column to the data frame. Okay. All right, so this is just a little bit of work into getting our data into a data frame from the thing. And so yeah, let's say we want to fit a linear regression model, okay? And so so what we're going to do is let's just take we're going to take the columns, we're going to take all of our columns except for price, throw that into our X matrix, okay, which is what we have here. And then we can also take just the price column, and that's going to be just the series. Okay, so what we can do now is we can fit our X matrix, okay, which is this, and it's already in the kind of the shape that we need. And as far as sklearn goes, scikit-learn is able to take in data frames as your X. It's going to kind of convert the data frame into a matrix and make predictions here, right? So we're going to just kind of fit the model. This is just fitting everything, okay, into the thing. So we do this, we get a linear regression thing. We can ask what are the coefficients. And so now we have a coefficient for all of these things. I didn't ask to fit an intercept. I guess I could have. I could have fit an intercept, but I didn't ask to do that. And so now we can kind of create our predictions based on these things, right? So this is a very, this is probably a model that's a little bit too big, and that this is just kind of the blind approach of like, you know, fit a linear model to all of your X predictors. And probably what we want to do later on is to do some kind of iterative method or some kind of model selection method where we're going to try to choose which features to keep, which of these X predictors to keep. Okay, but right now all we've done is we've just fit the entire X matrix to our data, right? So we're using all of our predictors. I think 13 of them, 1, 2, 3, 4, 5, 6, yeah, or 12, 13 of them into our thing. Okay, and so we can ask what are our predictions. We're going to ask make predictions for all of the values in our matrix X, and we're going to kind of compare this, right? So this is the difference. So how do you graph a you know, high dimensional data set, right? So here I've got 13 predictors. How can you graph all 13 predictors? Well, overall, all you can really do is you can say, all right, this is the actual value and this is what the predicted value is, right? So you've got all kind of 13 variables in your data set can end up kind of being predicted. So this is a comparison between what we predicted and what the actual value is. And what we're hoping to see is, you know, everything to kind of line up in a straight line. We do see some kind of strong linear relationship. We also see some strange artifacts. We get this flat line here. All right. And this is probably an indication of some kind of measurement problem. All right. So if you see something that looks like this, all right, and then when you look at your residual plot, okay, you also see some kind of straight line like this. This is an indicator that there's an artificial ceiling or cap in your data, okay? So for whatever reason, in our data set, the largest value that was measured in the actual column is 50, and it's consistently 50 across the board, okay? And so these would probably be outliers, probably the true value, something higher than 50, but for whatever reason, the person recording the data made some kind of decision that the value that we can, the largest value that can be recorded as far as this median value, is 50, right? It says variable 14 seems to be censored at 50. Okay, censoring is suggested by the fact that the highest median price is of exactly 50,000 is reported in 16 cases, while 15 have prices between 40,000 and 50,000. Okay, and it said the people doing the research didn't mention any kind of censoring, and so we don't really know. All right, but looking at this, when you see something like this, this is an indication that there's some kind of thing, right? And sometimes that happens in real life, right? Like maybe you have like a sensor, some kind of digital scale, right? Measures weight, and it has a max value. Like the heaviest thing it can weigh is like 500 pounds or something like that. And you're measuring all sorts of different observations, and you have some observations that actually weigh more than 500 pounds. but your your tools aren't able to measure that, right? So you just have to kind of max it out at 500, or you give it some arbitrary number and you have no idea. And so when you see something like that, you have to ask, like, what should the true value be? Should I even include these in the data set? Okay, so when you see something like this, that would be an indicator that, you know, there's some kind of problem there, right? Sometimes you get censoring on the lower side. You know, the smallest value you can record is maybe like 3 or something, and it's not accurate to record measurements under 3, or smallest value is, you know, some value, some arbitrary value. And when you look at your residual plots, you're going to see kind of these straight lines appear when you compare your predicted versus your residual. You know, how exactly do you handle that? There's also all kinds of questions there. Okay. So you can ask, the score overall is basically your R squared value between, you know, predicted and actual and things like that. This is just very, very, very basic as far as getting the basics in terms of fitting a model here. Okay. And as far as scikit-learn goes, right, this is linear regression, but pretty much any kind of model that you're fitting where you're predicting some kind of output numeric value, the regression, under regression, there's going to be all sorts of different things, right? There's logistic regression and all kinds of things, elastic net and lasso and things like that. And maybe you haven't learned those, maybe you've heard of those things. And all of those at its core, as far as executing it in Python and scikit-learn, is all done the same way. The only thing that's going to change is when you define your model, you're just going to change it from linear model.linear regression to perhaps you would say linear model.lasso or something like that. Okay. And effectively you can see, you know, as far as these codes go, you define your model here. Instead of linear model.linear regression, we got linear model.lasso, and then you do regression.fit, regression.predict. And this is effectively kind of how all of the scikit-learns, they kind of have a similar architecture. You define your model, you fit it to your training data, then you predict it on new points or whatever data you have. Okay, we'll cover a little bit more on scikit-learn, just some of the basic concepts here. And then so week 9, I'll do a little bit more on scikit-learn. We'll see how far we get. We can also do some kind of fun topics. I don't know how much you guys want. If you have suggestions for topics to cover in the last kind of week 10, I like to just do like this low pressure, like you don't actually have to learn this stuff, but it's like good to know. So I was thinking of including a little bit of SQL in week 10. I don't know if that is of interest to you. You know, and we'll just kind of say the stuff that we cover in week 10, I will not test you on, but it'll just be like, here's some stuff to learn. So we can do SQL, we can do web scraping, we can do stuff. I don't know how much we only have a few hours in there. So we'll take a look. Okay, let me give you your last view quiz answer for today. Last view quiz answer for today is the letter C. C as in cat. C as in cat is your last view quiz answer. Okay, so next week I'm planning on doing a little bit more scikit-learn. I'll also give you a description of what you can expect for the final exam. I'm starting to get a slightly better picture of it. Haven't done it yet, but I'll have a better picture of what you can kind of expect for the final exam. So yeah, we'll call that our last view quiz answer today is C. We'll end here for today, and have a good weekend, you guys, and we'll see you guys on Monday.